Hello, everyone. Welcome back to the video lecture series on atomic spectroscopy. In this final installment, we will be discussing the theories, key concepts, as well as the applications for atomic fluorescence spectroscopy. In this context, fluorescence means carries a different meaning. Well, in normal terms, fluorescence may refer to a individual who is energetic. In chemistry, it refers to the emission of light by a substance that has absorbed light or other electromagnetic radiation. Now, fluorescence is a form of luminescence, of course. And there are also other forms of luminescence, for example, phosphorescence, cryoluminescence, chemiluminescence, bioluminescence, such as those in the jellyfishes, and finally, radioluminescence. Now, AFS can be considered a combination of AAS and AES in a way that the excitation from the ground state to the upper state is carried out radiationally, such as that in the atomic absorption spectroscopy. But the measurement is made by uh, detection of as it relaxes back the radiation emitted by the atom of the excited state to the ground state. In AES, the atoms are excited only by collisional energy inherent in the high temperature of the atom cell, while in the AES and AFS methods, the atoms are excited primarily by radiation from a light source. Now let's take a look at an example of the experimental setup for AFS. Now, in this, the first step is sample preparation, whereby the sample is prepared in a liquid solution, done by dissolving the sample in a suitable solvent, such as water or liquid. Oh, sorry, water or acid. The sample solution should be clear, of course, of any suspended particles. Now, in the nebulization, the liquid sample is nebulized into a fine mist using a nebulizer. This is done by passing a stream of compressed air through the sample solution, and then it is then passed to the atomizer. Now, the atomizer converts the mist of sample drops into a vapor of atoms. So in this step is where the atoms are in an excited state, uh, which occurs after the atomization, whereby the EDLM, this is the same as interchangeable with the HCLM. So this excites the atoms at a specific wavelength specific to the element being analyzed. So after the atoms are excited, the atoms are now at a higher energy level. Now, the emitted light, sorry, the excited atoms emit light at a characteristic wavelength. The wavelength characteristics are determined by the electronic structure of the atoms, and the emitted light has a longer wavelength and therefore a lower energy than the absorbed light. Now, what does this exactly refer to? Well, I'll explain the statement. So it means that the atoms in a sample are excited by light at a wavelength that is specific to the element being analyzed. But when the atom emits the light produced is at a longer wavelength compared to the um, absorbed light. So that is a principle of atomic fluorescence spectroscopy. All right. So after this step, the emitted light is then detected um, and recorded. The data is detected and recorded. So here's a table comparing all three atomic spectroscopy methods. So basically, the sample polarization and nebulization steps are the same. The atomization of AS and AFS share the electrothermal um, method of atomization. In AS, the light is absorbed at a characteristic wavelength, while AS is emitted at a characteristic wavelength. But in AFS, the atom is excited at a wavelength, a certain characteristic wavelength. However, it is emitted at a longer wavelength. And finally, the detection for AS, it measures absorbance. AES, it measures the intensity of emitted light, while in AFS, it measures the intensity of, well, it's the same. It's the same as in AES. So, the theory of AFS is based on the quantum mechanical theory of light atom interactions. When an atom absorbs a photon of light, energy of the photon is transferred to an electron in the atom. This electron is then promoted to a higher energy level. So at, when it returns to its ground state, one moment, sorry, the electron emits a photon. So this is a diagram called a Jablonski diagram, which is a graphical representation of the electronic energy levels of an atom or molecule. It is used to explain the processes of absorption, emission, and fluorescence of light. The horizontal lines in the diagram represents different electronic energy levels. The ground state is the lowest energy state, and the higher energy levels are excited states. Now, this diagram is a useful tool for understanding the theory of AFS. It shows how the absorption and emission of light are related to the electronic energy levels of atoms and molecules. Now, on to the application of AFS. So this method is used in a variety of applications. One such example is in medical diagnostics, where it is used to develop new diagnostic tests for diseases such as cancer and Alzheimer's. It is also used to detect fingerprints, blood, and other evidence at crime scenes in the forensics field. In terms of security, it is used to develop new inks and dyes, which can be used to detect counterfeit documents and products. For example, maybe the inks in used to print money, currency, and it is also used in a lot of consumer products such as fluorescent lights, highlighters, and laundry detergents. So, in this video, we have discussed the key concepts, theories, as well as the application of AFS. That is all for this video. Thank you very much for tuning in, and I will see you next time.